Alright, so in this tutorial, we are going to go from the concept of electric fields and of electric field lines surrounding charges to quantifying or assigning a strength to the field when you're nearby a charge or a combination of charges. We're going to keep it simple and look at generally just one charge. But in our analogy of swag, in other words, if we have a person who creates swag, someone who just has an emanation, an aura about them, we know that the amount of intensity of that swag depends on how far away you are from them and the person himself. But we can define that intensity based on your reaction to it, but your role in it doesn't actually calculate into it. So that sounds confusing, because it is, but we'll try to work through it. All right? So what we want to do is define something called the strength of the electric field. This is not the same as force. Let me get that right out there. Force is the push or pull due to two charges. We're coming up with a quantity that depends only on the source of the charge and the source of the field. Okay, so there's a subtle difference there, but it's very important. Okay, so we want to come up with something called electric. Okay, we want a quantity that depends only on the magnitude of what we call field charges. Okay, and not what we call a test charge. So I'm going to call field charge capital Q. Then we're going to call test charge little qt. All right, little qt. This is to help us distinguish between those two. The equation we're going to develop ultimately depends on this guy, but we need this guy to actually feel the field, to feel how strong it is. Okay, so what we're coming up with is something called electric field intensity. All right, and it's given a symbol capital E. All right, that's not energy. It is electric field intensity, and again, it's not to be confused with force. So the definition of it is a very simple one, but it is very misleading. The definition of electric field intensity is the force that charges feel, Q1 and Q, divided by the test charge's contribution. Okay? So essentially what we're doing is we've got two Q's in the numerator. We want to divide out the influence of the test charge, just leaving us with this guy. Now in your reference tables, it's just going to be written as F over Q. Okay, I'm just trying to give you a little bit more insight onto that. So let's expand it out. We know F is equal to K Q1 times Q2, or little big Q times little q all over R squared. That's Coulomb's law. We learned that last week. So if I take this whole expression, and don't circle this, and put it into here, and I simplify, we find that E, we're going to see that the Q's cancel out right there, and we find that E is equal to K big Q all over R squared. Okay, and this is a lot more useful equation, except that it's not in our reference tables because the Regents doesn't expect you to use it, but I find it worth knowing about. So what we can see from this equation is that the strength of the field right there depends on two things. How much charge we have that's creating the field, in other words, big Q, and how far away you are from it. Notice that little q doesn't show up into this last equation, even though it appears to influence things there. It doesn't. So that's a tough little thing. You have to keep track of test charge versus field charge, and that's why I'm using the big Q's and the little q's. Anyway, the units, when I solve for electric field intensity, is easily derived from this equation right here. We have newtons on top divided by coulombs. Okay, so for example, if we were to have a field that was, let's say E was 10,000, usually they are a large number, newtons per coulomb. What that's basically saying is, let's say we draw the source of the charge, okay, let's say it's negative, and that's big Q. What we're saying is, for every coulomb of charge that we bring, little q, for every little coulomb that we bring, it's going to feel or require 10,000 newtons of force at that spot. So let's say I put it there. So if I bring 1 coulomb to this spot X, it will feel 10,000 newtons because of this field intensity that is emanating out in all directions. If instead I bring in a tenth of a coulomb, then E will still be 10,000 newtons per coulomb, but the force will be a tenth of that. So we'll try to do a little bit more with that later. Okay, again, important note, E depends on big Q, not QT. Okay. On the other hand, the force depends on both of them because you can't have a force without two charges. Do two examples. So what is the field intensity? E. We go to a different color. Okay. When a test charge, okay, that word test is important, that's little qt, is brought to a point, 1 meter, that's distance, from the static generator. So imagine our static generator charged up, and let's say that the charge on that is 2 microcoulombs. Okay, something we kind of derived the other day. Alrighty, so what do? I've got 2 equations for E. I've got this bigger one, and I've got the smaller one. What information do I have to help me solve it? Well, I know little q, so I could try to use this equation, but I don't have F, so I can't use this. If I want to use this one, do I know K? Yep, that's a constant. Do I know the field charge? Yep, we got it right here. Do I know how far away we are? Yep, so we're going to go with that equation. So I'd say the field intensity is K, big Q, all over R squared. Notice there's no little q here. We're not looking for force. We're just looking for intensity due to this guy only. It's only its contribution. So K is 9.0 times 10 to the 9th Newton meters squared per coulomb squared times big Q, which we said is 2 microcoulombs. So I got to change it micro to 10 to the negative 6th coulombs and divided by 1.0 meter quantity squared. Okay, so the denominator is easy because it's just 1. We work that out, and I suggest you type this on your calculator. You will find that the field intensity is 18,000 newtons per coulomb at a spot 1 meter. That's pretty high. Okay, so let me remind you what that number means. If we wanted to bring 1 coulomb, which is a huge amount of charge, to a spot 1 meter away from our static generator, it would require, or we would feel 18,000 newtons at that point. So if we wanted to bring a small charge to that, it wouldn't require as much force. In fact, let's look at that. How much force is felt at this spot? Okay, now we're looking for F. Well, there's 2 ways we can do it. We could do Coulomb's law, or we could use the idea that the field intensity is a given at the spot. It doesn't matter what we bring there, we know what E is. So if we know that E is equal to F over Q, little q, by definition, then I can rearrange that and say that F is equal to Q times E. That's why we define field intensity. It's a number that is a given for a particular location based on the source of the field itself. So anyway, what's the charge, our QT? It was 0.1 times 10 to the negative 6 coulombs. Our field intensity, we found out, is 18,000 newtons per coulomb. So we multiply those 2 numbers, and we get 0.0018 newtons. It's got to be newtons because it's a force now. So we see that even though the field intensity is really large 1 meter away, when you're bringing a standard test charge, the amount of force is going to be small. It takes, we're not going to be dealing with coulombs of charge. Now, what would change if QT doubled? In other words, instead of bringing 0.1 times 10 to the negative 6 coulombs there, we brought in 0.2 times 10 to the negative 6. Now, I don't want you to do the calculations all over again. I want you to understand this conceptually. So what I mean by this, how would E change and how would F change? Okay? As abstract as this, I'm hoping you're getting by now that E depends only on big Q. So there's going to be no change. All right? It doesn't matter what I bring to that spot. E is dependent on the field charge. What will change is the force. Because now I have twice the test charge based on Coulomb's law, which is proportional to both charges, we're going to have 2 times the original force. Okay? So we'll do more with that. If you have any questions, don't hesitate to ask when you come to class. All right, last problem we want to do is back to our parallel plates and our idea that with parallel plates we get a uniform field, which means everywhere inside the plate, the force field, the E is the same. So I'm going to draw field lines here. Just remind you, because we need practice with this. If I've got parallel plates like this, my positives are on the bottom, my negatives are on the top. So I would draw parallel lines, make them parallel, obviously, and evenly spaced. Okay, and what are we told about this situation? That the field intensity right there, E, is about 25,000 newtons per coulomb. Okay, that's a funny way of writing it, so let me write it like this. And now what we're doing is we're bringing a proton into the field. It's going to come in from the left, and I want to know how much force does it feel and in what direction. Okay, so imagine our proton is coming in like that, and then it's going to feel a force. Now let's do the direction. That's easy. The negatives are up here, the positives are down here, and so it's going to feel a force that is upward. Okay, it's going to be attracting the positive. Notice again that the force is in the same direction as the field lines. And the field lines are indicating E, the strength of the field. Okay, the force comes into play when we bring in another charge there. So I'm asking for F, well, and I know E and I know Q. Remember, Q of the proton is equal to 1 elementary charge, which is 1.6 times 10 to the negative 19 coulombs. So the force is pretty straightforward. F equals E times Q. Okay, E is pretty high, 25,000 newtons per coulomb, but we're bringing in a tiny amount of charge, 1.6 times 10 to the negative 19th coulombs of charge. And so we're going to get a really small force. That force, if we work it out, is 4 times 10 to the negative 15 newtons. Okay? Now, that might seem like a really tiny amount of force on a proton. We could then ask, what's the acceleration of that proton? And acceleration is A. Hopefully, you realize that if we know the force, we can get the acceleration is F over m. The proton's mass can be found in your ref tables, right in the front. Okay, you probably don't have them in front of you. I will give you the value, but understand that that's something you should be able to find. So A is F, a very, very, very small force. So you might think a very small acceleration, but the mass of a proton is 1.67 times 10 to the negative 27 kilograms. That's a really small mass. We divide them out, and we get a perhaps surprisingly large number, 10 to the 12 meters per second squared. Okay, so protons and electrons don't need a whole lot of force in order to accelerate them in large amounts. Think of the electron tube that I showed you the other day, where we had those electrons accelerating down in that tube. Right? They were feeling a force roughly the same as what I'm showing you here, but their accelerations were huge, and their final speeds were very large. Not quite the speed of light, but pretty close to it. Okay, so we'll stop here. We'll do some practice tomorrow, and then we'll finish up with some concepts of the electric field.